Okay, good morning, everybody.
Sir.
Good morning, sir. Good morning, sir.
Good morning, sir.
Okay, so today we have 100% attendance. All 19 are present. Okay, so we will start our session. So last class we have studied about the method of voltage control. Okay, so last class we have studied about method of voltage control. So under that we have seen that there are different ways which we can control the voltage. First, we can say it as a passive compensation is there. Then there are active compensation. So under passive compensation, we have done about the shunt reactors. Okay, and today we'll see with these shunt capacitors. Okay, so when you complete the shunt capacitor, so you know the difference between shunt reactors and shunt capacitors. Okay, so then you will also know what is meaning of reactors. Okay, so what reactors will do and then what capacitor will do this. Shunt, you already know shunt means it's connecting parallel, right? Series and the shunt. Okay, so you know this difference. So today we'll see on the shunt capacitors to control the voltage. Okay, so how to control the voltage using shunt capacitors. So actually this shunt capacitor will always supply the reactive power, whereas shunt reactor will observe the reactive power. Okay, difference you will see when you complete this shunt capacitors. Difference between shunt reactors and shunt capacitors you will know when you complete this too. So clearly you will understand what is meant by shunt reactors. Then when you will use shunt reactors and when you will use shunt capacitors, you will know after completing this. Actually, both of them are passive compensation because it has been connected permanently, right? So there is no automatic control. Even if there is automatic control, so this will fall under the passive. Okay, so normally these shunt capacitors will always supply, okay, it will supply the reactive power, which means it will inject the reactive power to the system. Why we are injecting? To boost the local voltages, which means we are controlling the voltages. If voltage is not at the acceptable limit, or okay, so if there is less voltage, then what it will do is, so we may have to inject the reactive power to boost the local voltages. In such case, we'll use the shunt capacitors. Okay, and then size of this shunt capacitor you will use will depend on your application. Okay, wide range of size we can use this, but this all are a little bit of the theory. So if you read by yourself also, you will understand that when shunt capacitor has been used, actually it has been started using 1910s for power correction. Okay, so yeah, as early as 1910s, and then towards late 1930s also it has been using, but moreover we are using now also. Okay, so but here if you read by yourself also you will understand, but very important thing you have to know here is what is the advantages, main advantages or principal advantages of using shunt capacitors, and then principal disadvantages of using shunt capacitor is a very important thing. Rest, these all are
Sir,
history. Okay, so these all are
sir,
the.
we cannot see the slide, sir.
Pardon?
Can you
Screen
see the
share.
slide, sir?
You are not able to see the slide.
No, sir.
No, sir.
Actually, I have shared. All of you are not able to see this.
No,
No,
sir.
sir.
No, sir.
Okay,
No, sir.
please wait. Okay, so then I will try to see. Actually, I have shared this slide. Okay. Okay, are you able to see this?
Yes, sir.
Yes.
Sir. Yes, sir.
Okay, okay. So actually I've shared. Okay, so now let me start again. Okay, so last class we have studied about the method of voltage control, and then under that we know that there are passive compensation and then active compensation. Okay, so there is passive as well as active, but still we are under the passives. Under passive we have studied with the shunt reactors, and then today we'll study on shunt capacitors. So now you will know the differences between shunt reactors and shunt capacitor clearly after completing the shunt capacitors. Okay, so basically, so both are the compensating device only, which will control the voltage, but one has to inject the reactive power, one will absorb the reactive power. So you will know when you complete the shunt capacitors which one will observe the reactive power and which one will supply the reactive powers. Okay, so now let's start shunt capacitors. Actually, shunt capacitors, okay, so it will supply the reactive powers and then boost the local voltage, which means if the system voltage is below the acceptable limit or acceptable range, then you may have to use the shunt capacitor so that you will bring back to the acceptable limit by supplying the reactive power. So yesterday I have asked what it will happen to the active power if reactive power is zero. So will it be feasible? Will it be desirable to have reactive power zero or not? So you will get from here. Okay, so actually, so if you clearly, if you listen carefully, you will get from here whether the reactive power can be zero or is it desirable to have reactive power zero. If reactive power is zero, what will happen to the active power? You will know from here. We cannot make the reactive power zero because if voltage level is low, again we have to supply the reactive power and boost the local voltage. Okay, so then if there is no voltage, then definitely if there is no voltages, then definitely you will not get the power because power equal to vi, right? Generally we can write P equal to vi cos phi, or we can write vi. So now if there is completely zero, reactive power is zero, then voltage will be zero. So now if voltage is zero, so now your active power as well as active power will be zero. So which means it is not desirable to have a reactive power zero, but it is also not desirable to have a reactive power as high as, okay, so we have to limit within the controllable range. Okay, so then, so just I have said about this. So these all are, okay, so these all are just history. Okay, so these are the history when shunt capacitor has been started using for power factor correction and then all. So if you read by yourself also, you'll understand. Okay, this one just I brought directly from the power system operation stability and control by P. Kundur only. So this one you can read. It's a history only. But very important thing is you have to know this one. Principal advantages of using the shunt capacitor and then principal disadvantages of using the shunt capacitors. So what is the advantages of using the shunt capacitor and then what is the disadvantages of using shunt capacitor? So if you know these advantages and disadvantages, then we can choose the appropriate compensating device. Okay, so now one thing is these principal advantages. Okay, so main advantages of using this shunt capacitor is actually it says in terms of cost it is cheap, low cost, and then this one advantage is low cost, and at the same time it is flexible of flexibility of installation and operation, which means wherever you require you can install this. Okay, so wherever it is required, if it is required at the load bus, then you can install and operate this one. This flexible allow us, okay, so it's the main advantages. Okay, so wherever required we can install and operate that. That's why, so this has a great advantages, which means they are readily applied at various point. Means wherever you require in the load bus, you can install the shunt capacitor to control the voltage at the same time, also power factor correction. Okay, so now if you are able to install, okay, wherever you require or in the point like load buses, it means that it is contributing the efficiency to the power transmission and distribution. So if there is some losses or if reactive power is becoming zero, so now you can install at that load bus, not from the source or at the end. Okay, so wherever you require, you can install, which will improve the efficiency of power transmission and distribution. Okay, so but every advantages has a disadvantages. We know that if there is pro, there will be a cons, right? Which means principal disadvantages of this shunt capacitor is their reactive power is very important thing here. Their reactive power output is proportional to the square of the voltage. Okay, this is very important. This reactive power output is square to the square of the voltage, which means, let's say reactive power R, and it is directly proportional to square of the voltages. So now what it happen is, so now if reactive power, let's say reactive power is reduced at low voltage, let's say there is a low voltages, then what it will happen is, so now reactive power is square of this, of square of the voltages. So what it will happen is your reactive power output will reduce at low voltages. If there is very low voltages, then what it will happen is, so now your reactive power output will decrease or reduce at square of this voltage. And then actually when we require a reactive power is when there is a low voltages. Okay, so when there is a low voltages, we require reactive power, but what it will happen is, this disadvantages is, since it is square proportional to the square of voltage, so now your reactive power output will reduce at low voltages when it is likely to be needed. When it is not required, let's say your voltage is within limit, so now you are not required to install a shunt capacitors. If you install a shunt capacitor, what it will happen is your reactive power will increase square of this voltage, and then what it will happen is, so now it will go beyond the acceptable limit. But when you are required is when voltage in the system is low, now you have to install the shunt capacitor. But one disadvantage it has is, so now when low voltage, again it is square of this, right? So means it will reduce, right? 0.1, let's say 0.1, if you square further it will reduce. So now this is a disadvantages, but advantages it has is, so it has a flexibility. Wherever you require you can install, and then moreover is cheap. So you know that when there is cheap, definitely there will be certain disadvantages, right? Cheap quality one will not have a good output, right? So that's why this is ways which we can control. But problem is, so its reactive power output is square, not directly proportional to voltage, but it is proportional to the square of their voltages. So it has a disadvantages of this. Okay, so you have to know this. Okay, so then let's see the application of shunt capacitors. You know the theory little bit on the shunt capacitors. So you know that it has to supply the reactive power to boost the local voltage, which means we can try to control. But advantages, we know that disadvantages is voltage is, its reactive power is directly proportional to square of its voltage. Okay, so it has a disadvantages, but even then, so now whether to choose shunt capacitor or reactor, or later on we'll see active compensation, which one to be choose, so it depend upon you. Okay, so how to choose that, and wherever it requires, it will depend on this. So now, but even then this shunt capacitor has a application. So basically there are two application of shunt capacitor. So first one is application to distribution system. So you know when we will call it as a distribution system, example 11 kV 11 kV feeder, and then all it will fall under distribution system. And then another application is application to transmission system. So now in distribution system, how we will use the shunt capacitor to control the voltage. Okay, so now most of time this shunt capacitor is extensively used. Okay, so generally it will be used in the distribution system, but it will also use in the transmission system. But now let's see how we will use in the distribution system. Okay, so basically this shunt capacitor is used in distribution system for two purposes. One is power factor correction. So you know how to correct that. Even you might have solved with one numerical example, that controlling of power factor. Okay, so now this shunt capacitor in distribution system, it will be used for two purposes. One is for power factor correction, another one is for feeder voltage control. Okay, so actually our main purpose is to control the voltage. How to control the feeder voltage? Let's say 11 kV. So now our desired one is 11 kV. We require 11 kV. How we will maintain 11 kV? So in distribution system, we can use this shunt capacitor and then get 11 kV. Okay, so now how we will get this is, okay, so now in distribution, okay, so we call it as this shunt capacitor as a distribution capacitor also, or either it will have a switched by automatic means, okay, it will have an automatic means responding to time clocks or to voltage or current sensing relays, which means, so in distribution system we will use this shunt capacitor and then it can be switched on automatically. Nowadays it can be on automatically. Earlier days there is a manual one where your operator has to go there and then put on or switch on the shunt capacitor, but nowadays we can do by automatic also. But how it will perform is, it will depend upon your voltage. If voltage is required to be controlled, then it will sense this their voltage is low or higher. Then if voltage is higher than the acceptable limit, what it will do is, it will just put off automatically. Your this shunt capacitor will be switched off. Okay, so now if voltage is low, your shunt capacitor will be automatically switched on, and then so it will try to boost the voltages. Okay, so now, but before that, let's see that what is the main objective of power factor correction. So as all of you know that why we have to do a power factor correction, and then so, but actually main objective of power factor correction is to provide the reactive power. Okay, so very important thing is to provide the reactive power close to the point where it is being consumed. Okay, so rather than supply it from the remote source, which what it means is, actually main objective of power factor correction is to provide this reactive power close to the point where it is being consumed. Okay, so which means if reactive power is consumed more at the generating side, then we can provide the shunt capacitor at the generating side, or if reactive power consumption is more towards the load, then we can connect to the load side rather than supplying it from the remote sources, which means rather than supplying it from the one sources. Okay, so it will not be connected at the one source. If it's connected at the one source, so now we never know at that source power factor might be good. Okay, so but what it be done is, main objective is wherever reactive power is consumed, okay, then we will try to install the shunt capacitors. This is a main objective of power factor correction. Okay, so but we know that most of the load will observe the reactive power, so that's why you will see that shunt capacitor or capacitor bank at the load side or industrial side, not at the generating side. Okay, so we know that most of the load will observe the reactive power, so that's why you will see that most of the capacitor bank at the load side, or most of the load will have a lagging power factor. Okay, so why? Because most of the load observe the reactive power, so that's why you will find that most of the load will have a lagging power factor, not a leading power factor. Okay, and moreover you will also find that this shunt capacitor or capacitor bank will be at the load side or industrial side, not at the generating side, because most of the reactive power will be observed by the load. Okay, so now with one example, so just I have taken out from the Kundur book, that these are some typical load. Okay, so like large industry motor, what is a power factor? So normally this power factor, normally it will be a lagging one. Okay, so this will be a lagging one. Okay, so it is a large industrial motor. So just one typical example I have taken out from the P. Kundur book. Okay, and then small industrial motor. So power factor will be generally this much. Okay, so this is a general one. Even color TV, fluorescent lamp, lighting, incandescent lighting. Okay, so now normally incandescent lighting will have power factor 1. So you might be knowing why it is, right? Incandescent lighting. So you might be knowing this. Okay, so now if you have forgotten, then please try to find out from electrical workshop why incandescent lamp is having a power factor generally at 1. Okay, general, I'm saying, okay, generally it will have this, and then this load will depend on voltages, voltage dependent, both active as well as reactive power. So do we know that it will depend on voltages? Okay, so except incandescent lamp and then range or water or space heating, so rest all will depend on the system voltages. Okay, this is just one typical example I have taken out from the book, which I want to show that. So most of the load will consume the reactive power, so that's why you will find that most of the load will have a lagging power factor. So example, like in large industrial motor, it will consume or absorb the reactive power, so it will have a lagging power factor. So general one I have given 0.89. Okay, so this general, and then it will also depend on the voltage, both active and reactive power. Okay, so now how to use this in the distribution line? Okay, so you know the characteristic of this capacitor in the distribution system where you will use, and then even you know the load characteristics. So now how you will apply this shunt capacitor in the industrial plant, or let's say one industrial plant. Okay, so now let's assume this is a power factor correction in industrial plant or one industrial plant. So let's say here utility means supply is here from BPC. Okay, it's a source here, utility supply, and then let's say here we have a plant characteristic. Okay, so plant has a lot of load, but here I have just assumed that induction or motor only. Okay, so most of the plant will have a motor. So example, so now before compensation, if let's forget about the compensation, but let's think that from here utility, so let's assume that here it is a 66 kV line supplied from BPC, and then or from this 66 kV, everything has to be taken care by the plant, right? So now from till here BPC will supply, then from here you may have to step down, and then you may have to get 33 kV. Okay, so 33 kV here, and then similarly you may have to step down to 11 kV, and then further you may have to do based on our requirement. But this is without the compensation or without installing the shunt capacitor. But how you will use shunt capacitors? Because you know that in this industry most of the load are inductive in nature, and already we have said that most of the load will absorb the reactive power, which means it will have a lagging power factor. Then you know that if you have a lagging power factor or low power factors, so normally you will have to pay a penalty for power factor, right? So in this consumer, so BPC is charging for reactive power as well as active power, right? So that's why if there is some compensation, so some incentive will be provided by the utility. So now how to carry out this now? There are different ways which we can compensate this reactive power consumption. Okay, so now how we will compensate this? One option could be individual motor. So you can connect here in all the motor. So you can try to connect the shunt capacitor like this, which we call it as a individual compensation. Okay, so you can do by this, and then so you can compensate or you will try to improve the power factor. But problem with this one is everybody will agree with me that it will be very costly. So there will be a lot of motors, induction motors in the industry. So we will not be able to connect to all the individual motors. So now another option could be, so now instead of connecting to individual motor, so from group of motor you connect one shunt capacitors. So this is known as a group compensation. Okay, so to improve the power factor you can do this individually, you can connect, but if you are wealthy enough or if you have a huge money, then you can invest such case, it will be much better. But what we have is that the problem here is, so it will be very costly, which most of us will not be able to afford this. So what we will do is, so now in a group we will try to compensate. So that is known as a group compensation. So there will be a huge number of motors. So for that one, we'll try to connect one shunt capacitor. So then this will also function for improving the power factor. Okay, so this is second option which we can do. Another option could be, so you can connect to this whole system, okay, by use, and then you try to, so if you connect here, okay, shunt capacitor here, so it will control the power factor of all, okay. Then if you connect here, so it will control for this all, right, from here, no need to connect these two. If you connect this one, so now that is known as a plant compensation, means overall plant compensation, okay. So there are different ways which we can do, but more efficient one will be individual compensation. But individual compensation, efficiency wise it is good, but cost wise we will not be able to afford that. Then if you are not able to afford that one, so you can go for group compensation, okay. So you group the different motors, okay, in a different location and try to compensate by connecting a shunt capacitor parallel to this. Then if you are not able to afford this also, then what you can do is you go for whole plant compensation. So most of the industry, so in Pasakha or wherever there is industry, you will not find that individual compensation. Moreover, even group compensation, I have not found it. What I have seen is one capacitor bank in the whole industry, and then they just connect to the whole plant, and then they try to compensate the power factor. This is because individual compensation is very costly. Even this group, it found to be very expensive for them, because all the private company are, they are driven for profit, right? They want to have a more profit only, so that's why, so it might have a huge losses to them, because it has to have a huge expenditure on this all. So then most of time you'll see, but these are the ways which we can control the power factor, or try to improve the power factor. So now our question is, what is the relation between power factor improvement and voltage control now? Okay, so actually, so this is a power factor improvement which we can do. At the same time, what you can do is by connecting here, first option is, so you are trying to improve the power factor. So now at the same time, so from here, we can call it as some feeder wall line. So we can also control feeder voltages. So which means, as example I have given here 33 kV. So here we have to maintain at 33 kV, which is a acceptable limit, right? If it is below 33 kV, then it will not be a within a acceptable limit, which means if you prolong using this one, what it will happen is your motor will get damaged, or it will not function to full efficiency. Your production may go down. So now if you connect like this, so first thing is it will improve the power factor. At the same time, so what you will get is you will also control the feeder voltages. If it is low voltages, then what it will happen is the shunt capacitor will boost the voltages, increase the voltages, and then so it will bring to the acceptable limit. Okay, then okay, so they are installed at appropriate location at length of feeder. So actually, so this is the diagram which is used for compensation of power factor. But if you want to control the feeder voltage, then there will be at the appropriate location where there is a feeder, so you can connect this shunt capacitor and then try to control the voltages. Okay, so now what it will do is at all point and remain within the allowable maximum and minimum limit as the load varies. So now, so here in this diagram I have shown only for the power factor improvement. Similarly, you can draw this, and then you draw a lot of feeders here. Okay, so and then you connect to the appropriate feeders. So you can do an individual feeder compensation, group, you can group the feeders and then do a compensation. Also you can do a whole feeder, but most of time, okay, see in our industry we'll see only for a power factor improvement, not for the voltage control. But even we can do a voltage control, and then we can maintain voltage within the allowable maximum and the minimum limit, okay, so as the load varies. Okay, so this is the application of shunt capacitor in distribution system. Okay, so one thing. Then another application of shunt capacitor is in the transmission system. Okay, even it can be used in the transmission system. Okay, so this shunt capacitor in transmission system, mostly it will compensate the I square X losses in a transmission system, so that your voltage level during heavy loading condition should be at the satisfactory level, which means there should not be any parenting effect, which means sending end voltage, receiving end voltage should not be greater than sending end voltage, but sending end voltage and receiving end voltage should remain same, means there should not be any voltage drop. So when voltage drop will take place is when there is I square X losses, then there will be a voltage drop. So to prevent this one, we try to use a shunt capacitor. But if there is Ferranti effect, it by anyhow it has happened a Ferranti effect, then what you can do is you have to switch on the shunt reactor, right? So which will try to observe the reactive power and then try to maintain the voltage at the acceptable limit. Okay, but just now since we are talking about the shunt capacitors, so just we are seeing that we don't want to have a low voltage at the receiving end. Okay, so when it will happen is when there is voltage drop in the transmission line. When voltage drop takes place is when there is I square X losses in the transmission system. So now in transmission system we use basically to reduce or compensate for losses taking place in the transmission line, so that our losses voltage level will remain at the acceptable limit even if there is a heavy loading condition. Okay, so now the size of capacitor, it will depend upon the individual, where how much, what is the size of the capacitor requires, it depend upon how much you want to compensate this one. Means theoretically we have to calculate, but just now you know that it is only application, so now we can connect this, and then you know that capacitor bank of appropriate size can be connected. Okay, so here there are two ways which we can connect the capacitor bank. Okay, so one, by using one transformer, and then I said that you have learned transformer, and transformer with three terminals. One is call it as a tertiary transformer, mostly for harmonic. Okay, so reduction of harmonic, there we have to do this. So now we can connect through this one using a transformer. Okay, tertiary connected capacitor bank, or you can do directly to the HP capacitor bank, or we call high voltage capacitor bank. You can connect directly to the buses, which it will have. Normally transmission system is high voltage, right? So that's why it has written high voltage capacitor bank. Okay, so they are using one breaker and then switch. Okay, switch it either automatically or by voltage relay, or manually also their option. But nowadays we are going automatically by using a voltage relay, which means you have to employ a voltage relay where if voltage is below the acceptable limit, what it will happen is it will try to switch on this and then boost the local voltage. Okay, so which means so it will try to maintain at the same voltages. Okay, and if it is more, then it will try to switch off automatically. Okay, so before or earlier days it has to be done manually, which means we have to measure at the end, and then if voltage is low you have to go there and switch on, and then if there is less voltage, if there is more voltage, you have to switch on off here. So but nowadays it has become a automatic because of the development of this relays. Okay, so there is a voltage relay which will sense low voltage or under voltage, and then our capacitor bank will be switched on. Similar case here, even for connection of this it will remain same. So this is how they will try to minimize the losses in the transmission system, or compensate whatever losses is taking place in transmission system by employing the shunt capacitor, so that we will try to maintain at the acceptable voltage limit. Okay, so they are normally distributed throughout the transmission system so as to minimize the losses and voltage drop. Okay, so this shunt capacitor in a transmission system will be distributed throughout the transmission system, okay, to minimize the losses and voltage drop. But now in our system, so we will not find this all thing, but this all can be used to, okay, compensate the voltage losses and then control the voltage in the transmission system. Okay, so this, so one option. Okay, so there are two application of the shunt capacitor. One is in the distribution systems. Under distribution system, so we can control the or give power factor, at the same time we will control the voltage. In transmission system, so normally we will not look for the power factor as such, but what we will do is we'll try to see that how to compensate the losses. Okay, how to compensate the losses So this one, by connecting a capacitor, so we will try to compensate the losses. How we will compensate the loss? We'll try to minimize the voltage drop in the transmission line by connecting this. Okay, so this is how we can use the capacitor in a transmission system. Okay, so are you able to get this? Okay, so these are the two applications of the shunt capacitor. Okay, so today, okay, so we still have some more time. So with this, so I will try to introduce next unit. So next unit also it is a compensation only. Okay, so but next unit we will see the active compensation. Okay, so passive compensation we have started already over. Okay, so just we have done for shunt reactor and shunt capacitors. So now you know the difference between shunt reactors and shunt capacitors. So now next lecture will be on the excuse me, so there is some technical problem in my system. Okay, so next will be on the static var system. Excuse me, there is some problem with my laptop. Please bear with me. So there is some problem with my system. So laptop, it has hanged now.
Okay, sir. No problem.
So you know, right? So condition of my laptop.
Yes, sir.
Are you able to see this one? Static var system?
No, sir.
No. So there is some
sir.
problem with my system. I don't know what it has happened. Okay, so are you able to see this static var system, lecture 4?
No, sir.
No.
No,
No,
sir.
sir.
Okay, so
No,
there's
sir.
some problem.
No.
Okay, thank you.
Now visible, sir.
Okay, are you able to see now?
Yes, sir.
Yes, sir.
Okay, so still we have some more time. So we have around 15 minutes. So for this 15 minutes, we will try to introduce this static var system. Okay, so this is also a voltage control only. Okay, so under voltage control, we have learned that there are two ways which we can control: active and passive. So active will fall under static var system, and then passive already we have completed shunt reactors and shunt capacitors. So if you employ shunt capacitor and shunt reactors, so then it will fall under the passive compensation. Whereas if you use a static var system or SPCS, so it will fall under the active parts. So now, so in power electronics, okay, so already you might have learned about the static SPC devices, like already you might have learned fax device and then all. Okay, so we will not go that detail of the fax device characteristic, waveform. Little bit we may require, but we will not go that detail VI characteristic and then all deriving that equation. But what we will do is here we will use that fax device to control the voltages as well as power factor also. We will see simultaneously, but as per syllabus, it says control of voltage and the reactive power. If you are able to control the voltage, definitely you will be able to control the reactive power. It has a link. Okay, so but we'll see how to improve power factor also. But this static bar system characteristic, like example thyristor, control, everything you might have learned in the power electronics. VI characteristic, everything you might have learned in the power electronics. But here we will not derive that equation VDC or IDC. But what we will do is we'll try to use that device, that characteristics in the control of voltage and reactive power. So now this static VAR system is will fall under the active compensation. So before we start about the static VAR system, so little bit of terminology in static VAR system you have to know. Okay, so we have to be very careful about this terminology. So there are different terminology used in the static VAR system. So one, SVCS, that is static VAR compensators. Okay. SPCS, then you will see SVG, then you will see MSC, and then MSR, and so on. This all you have to be mindful of this. Okay, so when we use this, what is mean by SPCS, what is mean by SPS, what is mean by SPG, you have to know this. So before I start about the static VAR system, so first I'm introducing some terminology used in the static VAR system. So in static VAR system, these are the common terminology which we will use. SPCS. What is SPCS? It is a static VAR compensators. Okay, it is known as static VAR compensators, and it is a shunt connected static generator. Actually, it is a shunt connected static generators or an observer whose output are varied as to control the specific parameter of electric power system. Okay, that SPC is actually it will be shunt connected. It is static generator as well as observer. Means it will act as a generator. At the same time, it will try to observe the reactive power depending upon which one you want to control. Okay, whether you want to control power, whether you want to control the reactive power or voltage, or whether you want to observe the reactive power or generate the reactive power, depending upon the specific parameter of electrical power system. So we'll employ this SPCS. Whereas earlier one, you might remember shunt reactor, it has to observe the reactive power, whereas shunt capacitor, it has to supply. That you have to know. But here SPCS, we call it active because whenever required, it will generate the reactive power. Whenever required to be observed, the reactive power, it will be observed automatically based on the condition of our electrical power system. So nowadays, that's why these SPCs, okay, so power electronic devices are becoming famous because of this property. It can act as a generator as well as observer. Okay, now you know the term static itself means it will indicate that it will not have a rotating part or moving part. Okay, so and then you have already learned about the synchronous compensator, means synchronous condenser. Like you might have done in that there will be a moving part, but unlike synchronous compensators, SPCS will not have a moving part, which means that's why it has given a static. Okay, then SPC consists of static VAR generator or observer. So now static VAR generator is normally we will abbreviate as SVG. Okay, so in exam it may not come as what is mean by SVG, but you have to know if somebody asks, okay, what is SPG, and then in the question it was been given SPG and then SPC. So you might have to know this little bit differences. That's why I have given here. Okay, and then it will observe the device and suitable control devices. Okay, so then another system terminology it has been used in SPC is static VAR system. So you have to know that static VAR system differences and SPCS. Actually, this static VAR system is a aggregation of the SPCS. There are different types of SPCS which we will learn later, and all these types of SPC will fall under the static VAR system. Okay, so what are the types? I will explain later. Okay, so there are different types of SPCs. These all SPCs will fall under the static bar system. We call it as a static bar system. And mechanically switched capacitor, okay, so will come at MSC, or reactor will come MSR. Mechanically switched reactors, and another one is mechanical. Okay, so whose output are coordinated this. These are the basic terminology which we will use in this static bar systems. SPCS, okay. Under SPCS, we learn again further. There are different types of SPCS, but what is meant by SPCS? So you have to know that it is shunt connected static generator or observer. And static means it will not have a moving part. Under SPC, there will be generator, SPC generator, and the observer. Then you have to know the difference between SPS. Actually, it is a aggregation of SPCS, which will have this mechanically switched capacitor or reactor, whose output are coordinate based on. These are some terminology, basic terminology, which we will use in static bar system. Now there are different types of SPC. Okay, so there are different types of SPC. Basically, there are many types of SPC. Already you might have came across this in power electronics, like thyristor controlled. Okay, so except reactor, you might have seen about thyristor control, thyristor switch. Okay, thyristor switched reactor, thyristor control transformer. Okay, so here what it will do is, so you have to use the, okay, so we have to use the thyristor, and then we can control the output of the reactor. Reactor normally is, so you know that reactor which will observe the reactive power. So which means generally inductance will fall under the reactor. So you'll connect one reactor with the SPC, like thyristor control. You know what type of thyristor is. Okay, thyristor control. So it will fall under the thyristor control reactor, TCR, or saturated reactor also there. So most commonly is this one. Then another one is thyristor switched capacitors. Okay, you can use this. Okay, thyristor switched reactor also we can use this. Then thyristor control transformer, and then another one in power electronics. I think you are now studying about the power electronics application, but power electronics already you have completed. So you might have heard about self or line commutated converters, SCC or LCC, right? So now these are the basic different types of SPC, which we will be used to control the voltage, at the same time try to improve the power factor. So all this will fall under SVS, that is static var system. But these are the SPCS, static var compensators. Okay, these all different types of SPC will fall under the SVS, which means static var system. Okay, so there are different types, and already you know the characteristic of thyristor. So we can employ thyristor and control the reactor. So we do call it as a TCR, thyristor control reactor. You can employ thyristor and then switch this capacitor. So we do call it as a thyristor switched capacitor. Similarly, you can use a thyristor. Okay, so this power electronics device, and then what is self or line commutated converter. So you might have learned this, but we will not go in detail of the characteristic of thyristor. Okay, so we will not go detail of the characteristic thyristor. This already you have learned in the power electronics. So what we will do is, so we will draw one thyristor control reactor. Example I'm giving here, thyristor control reactor, and then we will try to control the voltage at the same time power factor in either in distribution system or transmission system. How to control that? This is our main focus. Okay, so now there is misconception by our student that there is repetition when somebody say something about the thyristor. So your senior batch has said that there is a repetition of power electronics in the power system operation and control. Actually, it is not a repetition. So this part thyristor characteristic, we will not study about this characteristic. How it control, we will not we will not study about how this thyristor will control and then all, but what it will do is, so we will see the thyristor control reactor. Your characteristic is already known. Reactor means which will observe the reactive power. Inductors, normally inductors will fall under the reactors. So now you try to connect either series or parallel is thyristor, and then you can connect parallel with your system, transmission or distribution system. Then we'll see how it will control the voltage and improve the power factors. So characteristic of thyristor will not be learned, so you don't get misconception with this. Okay, so most of our students said it is a repetition. Actually, it is not a repetition. Here we'll see the application part, not the characteristic of thyristor, and then not the characteristic of self or line commutated converter. Okay, so this is about the different types of thyristor SPC system. Okay, so there are different types of SPC system. Basically, there are many. Okay, so but I will go through as per our syllabus. We will go through few of them. Mostly thyristor control TCR, TSC, TSR, and then TCT. Also, we may see that, and then we'll see SCC or LCC, and then we'll see how we can control the voltage and power factor by using this device. Okay, so now let's so now, so for today, I will stop here because we have left with only 4 minutes. So now I will stop here. So tomorrow we will start with this fundamental frequency performance of SPS. So we'll not go directly to the SPC individual component. First, we'll see how this system will control the voltage. Okay, so system is SVS, static bar system. Okay, so which will fall. Okay, so under that there will be different tests, but first we'll see how it will. Okay, first the characteristic of SPCS, then we'll see the characteristic of realistic. First we'll start from ideal, then real SPCS, then power system characteristic also we have to know, then only we will be able to choose which SPCS is suitable for this. Then we will see the composite together this characteristic, and then we'll try to end up by the fundamental frequency performance of SPS. So then after that, so this is general about the SPS. So then we'll see under SPS, one SPCS, different types of SPCS will fall under SPS. So we'll see one by one that different types of SPS in the next session. Okay, so for today, we'll stop here. So, okay, so that's all from my side. So if you have any doubt, so you can ask. If you're not able to ask in a group, so you can just drop in my personal mail or VLE, or now we have created WhatsApp also. You can try drop there. So whatever possible, I will try to answer immediately. If it's not possible, then I may take 1 or 2 days, and then I will post in the WhatsApp group for the benefit of whole class. Okay, so that's all for today. So thank you for coming online.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay, so thank you, and stay safe.
Thank you.
Okay, sir.
Thank you, sir.
You
Okay.
too, sir.
Sir,
Thank you, sir.
assignment where we have to submit, sir?
So you can submit. I will create in the VLE. You can submit, and then there is option. If you're good in typing, you type. If you're not able to type, you can write by hand. Okay, and then just scan and then make PDF and then say upload in the VLE.
Okay, sir.
Okay.
Okay, sir.
There
Okay,
is
sir.
option. If you're good in typing, very fast in typing, you can type. I think it will be very difficult for all of you to type. It is mass equation will involve. You write by freehand, scan by mobile. Now smartphone has a facility, so you can submit that. And then again, I will download here, correct, and I will scan and then upload there. Whatever it is wrong, I will try to correct this. Okay.
Okay, sir.
Okay. Thank you. Thank you for coming online.
Sir.
Okay.
Thank you, sir.
Thank you, sir.